a good example, is heartbeat. Heartbeat, many people think, is class 2, very clockwork-like. It's not. It's actually class 4, which I'll tell you about next. Class 2 heartbeat means that you're about to have a heart attack. If a EKG technician sees class 2 behavior, they automatically call the doctors because it means a heart attack is imminent. Too much regularity is pathological. Heart attack is class 3. It's where the muscles of the heart beat chaotically and don't pump blood efficiently. So where you really want to be is in between class 2 and class 3, in between too much order and too much chaos. And that is class 4. Class 4 is called the edge of chaos. It's in between class 2, which is very orderly, and class 3, which is very chaotic. It's also called the K-ord, which is a contraction of chaos order. K-ord. It's the boundaries between order and chaos, and it's characterized by something called power laws and fractals that I'll tell you about briefly in a moment. Virtually everything in nature is class 4. We don't know why yet. This is a fact that we've learned over about the last 2 or 3 decades. Everything in nature, including all of your physiology, is class 4. A healthy system is class 4. Not too much order, not too much chaos, but sort of in between. Here is an image that graphically represents what I mean by the edge of chaos. This black region over here, oh, by the way, this is an image that is manifest from a very, very simple nonlinear equation. You're looking at a colorful graph of that equation. In the seminar, I talk about what the equation is and how it works. It's very, very easy. Over here on the left, in this black region, all these black regions here is high order. The system is behaving in a class 2 fashion, very orderly. Up here in these green regions is chaos. It's very chaotic. The system is not behaving in any kind of orderly fashion at all. These red and purple regions right in here, in between black and green, that is the edge of chaos. And you can see how complex it is. Extremely complex. One of the characteristics of class 4 systems are called fractals, which I'll show you here in this next slide. Fractals are simply defined as objects or images that are self-similar on many scales. Now, translation into English, that means that the parts look like the whole, and the parts of the parts look like the whole, and the parts of the parts of the parts look like the whole. Self-similar on many scales. Nature is full of fractals. Take a little part of this fern and magnify it, looks like the whole fern. Take a little part of this cloud and magnify it, looks like the whole cloud. A small part of the tree looks like the whole tree. And branches of this branch look like the tree, etc. That's fractal. Class 4 systems are also said to follow something called power laws. In the seminar we go into detail about this. It's not hard. The basic idea of power laws is that you relate the size of an event to its frequency. The size of an event has a relationship to frequency, and in a power law distribution, big events are infrequent, whereas little events are very frequent. Big ones happen infrequently, little ones happen all the time. Little earthquakes in Los Angeles every day, very frequent. I'm going to do that differently. Little earthquakes, very frequent. Big earthquakes, fortunately, infrequent. Avalanches, climate changes, species extinction, stock market changes, all of these things work on power laws. Little changes usually, occasionally you get a really big one, intermediate for intermediate size. Everything in nature appears to work on these power law distributions. Again, we don't know exactly why yet. So if you see power laws in the time series of a system and fractals in the structure of the system, you say to yourself, that's a class 4 system. Power laws and fractals are characteristics, if you will, of class 4 systems. So next, after a break, I want to talk a little bit about climate change, and what I'm going to do is apply the ideas that I've talked about in part 1 to help us understand climate change in a more realistic way. And so I'll take a break now.